Hello and welcome to Lab 11. This is the Titration lab and I am Dr. Ratnayaka. As you can see in the equation, we have our acid, which is KHP, being added to our base, which is NaOH or sodium hydroxide, to produce water and a sodium salt. Notice that there is a 1-to-1 mole ratio here, meaning that every 1 mole of KHP is neutralized by 1 mole of sodium hydroxide, which means if we know the moles of sodium hydroxide at the neutralization, then we know the moles of KHP as well, because it is the same. As you see in part 2, we have a very similar role. So we have the moles of sodium hydroxide being in the same ratio as the moles of vinegar here. So every mole of sodium hydroxide that we drip into our vinegar is going to neutralize it. So let's take a look at some example calculations on how to do part 1. So in part 1, our objective is to standardize the concentration or the molarity of sodium hydroxide. Since sodium hydroxide is a hygroscopic solution, meaning that it readily takes in water from the atmosphere, we need to be sure that we know exactly its molarity before we do part 2. So in this example, we say that we have 1 gram of KHP, and based on the fact that the molar mass of KHP is 204.22 grams per mole, 1 gram of KHP is about 0.0049 moles. Because of our chemical equation, we know that there is a 1-to-1 mole ratio of KHP and sodium hydroxide, which means that if it took 23 milliliters of sodium hydroxide to titrate that KHP, that means we also delivered 0.0049 moles of sodium hydroxide to that solution. So to figure out the molarity of that sodium hydroxide, we take those 0.0049 moles of sodium hydroxide we know were delivered and divide that by the volume of sodium hydroxide, which is 23 milliliters or 0.023 milliliters to get 0.213 molar sodium hydroxide. In part 2, we will use the now known molarity of sodium hydroxide to figure out the molarity or concentration of acid in a vinegar bottle. So to do this, we will use a diluted amount of vinegar. We'll take 10 milliliters of vinegar and dilute it 10 times, i.e. we will add 90 milliliters of water to it, and then we'll use 10 milliliters of that 10 times diluted vinegar and titrate that with our now known concentration of sodium hydroxide. Since there is still a 1-to-1 mole ratio of vinegar to sodium hydroxide, once we get to the equivalence point, we will have the same amount of moles of sodium hydroxide, the base, and vinegar, the acid. So for this example, we're going to be taking that 10 milliliters of diluted vinegar and titrating with 11 milliliters of sodium hydroxide until it reaches the endpoint. You see that 11 milliliters of sodium hydroxide will give us approximately 0.0023 moles of sodium hydroxide. Now that we know that we have a molarity of 0.213 moles per liter of sodium hydroxide. Since it's a 1-to-1 mole ratio, if we have 0.0023 moles of sodium hydroxide, we also have 0.0023 moles of vinegar. Now that we know that, we can take that and divide it by our volume of vinegar in our container. So our original flask has 10 milliliters of our diluted vinegar. We convert that milliliters to liters, and we see that our concentration of vinegar in our Erlenmeyer flask is 0.23 molar. However, that Erlenmeyer flask contains 10 times diluted vinegar from the Publix jug. So to figure out the concentration of the vinegar in the Publix jug, we take our concentration from our Erlenmeyer flask and we multiply it by 10. Therefore, that means that the concentration of vinegar in the Publix jug is 2.3 molar or 2.3 moles per liter. So in this lab, we have several materials that we'll be using. We're going to start off by looking at our burette and our burette sand. A burette is just there to hold liquid and allow us to drop a liquid bit by bit into a container. The container is going to be our Erlenmeyer flask, as you can see here. The shape of the Erlenmeyer flasks allows us to minimize spillage and splashing when we drip the drops from the burette into the Erlenmeyer flask. In addition, we have our scale, which is accurate enough to measure in 0.01 grams. Along with that, we have our weigh boats and a squirt bottle in which we will have our phenolphthalein solution. So phenolphthalein is our indicator in this case. This means that this is the actual chemical that will change color when we go from acidic pH to basic pH. Without this, we would not see any color change during this. In addition, we have our base, which is sodium hydroxide, you see here, and that will be about 0.1 molar or 0.1 moles per liter. We make a solution by taking 0.1 moles or 0.1 moles of NaOH and dissolving it in about 1 liter of water. Our acid will be the KHP or potassium hydrogen phthalate, and that is shown here in solid form. And in addition, our secondary acid will be our Publix brand vinegar right here. In addition, we have our volumetric pipette, which will help us deal with precise measurements you see here. This volumetric pipette allows me to slowly increase the decreased volume taken and gives us very accurate results based on that.
All right, so for part one, we're going to start by adding our base, our sodium hydroxide, into our burette. We're going to try to fill it all the way to the top. Now this burette can hold a maximum of about 50 milliliters of liquid, and we're going to try to get to as much as that can. The important thing about this burette, as mentioned, was that it's backwards. So our recording volume is going to be 14, as you see here. And next, we're going to go ahead and weigh out our KHP. We need to first zero our scale and then mass a amount of KHP, our known acid in this case. So we'll go ahead and carefully add some KHP to the scale and the balance. So we'll go ahead and record our mass now of KHP for trial 1. Now we will add about 50 milliliters of water to an empty Erlenmeyer flask here. So you see us do that up to about the 50 milliliter mark. Now the amount of water doesn't really matter in this case. We're just using it to dissolve our KHP. What really matters are the moles of KHP, or the moles of acid that we end up using. We've got to make sure to get all of our KHP inside. You'll see its granules forming at the bottom there. Now we want to homogenize this mixture, so we're going to swirl until all of those crystals dissolve, as you see here after some time. Perfect. We'll then go ahead and add our phenolphthalein to this solution. So phenolphthalein is our important indicator. It is what actually causes a color change when we raise our pH. So right now, the pH in this solution is very acidic because all we have is our acid. We're going to change that by slowly opening our stopcock and putting base into our acid, drop by drop, to make sure that we don't go over the endpoint, which in our case will be when the moles of acid equal the moles of base. So right now there are more moles of acid in this solution than moles of base, but we're slowly increasing the moles of base. Once the moles of acid equal the moles of base, we should see a color change, and that signifies we've reached the endpoint. We're going to keep on swirling because if we stop, you can kind of see the purplish color start to appear a little bit at where the drops are hitting the liquid. So I'm going to keep on swirling momentarily just to make sure that we have a completely even purplish pinkish hue, not just at one spot in the solution. So constant swirling makes sure that all of the ingredients are equally distributed throughout this Erlenmeyer flask. You can see if I stop for a second, we start to see that purplish color appear, but it's not the right kind. And it helps that it's behind or in front of a white background, so we can see that color change very clearly when it does happen. All right, it's starting to happen right there. So we're going to stop the base dropping, and there we go. Look at that nice pinkish hue. So now the phenolphthalein has told us that we've reached pH 7 and our endpoint. So this is our final volume of sodium hydroxide. Go ahead and record it in your notebook. And we'll go ahead and do a second trial of that. As the beginning, we go ahead and weigh out some KHP. We'll record its mass. We'll add some water into this Erlenmeyer flask so we can go ahead and dissolve that KHP. That's phenolphthalein, mix it around, homogenize that, and we'll record our starting volume for our sodium hydroxide. And we can go ahead and start dripping our sodium hydroxide into our KHP while swirling to make sure that everything is homogenized inside of this Erlenmeyer flask. Now, as we get closer to the endpoint, we'll slow the drip down. Keep on swirling, and there we go. Here's our endpoint. You see that nice color there. And our final volume of sodium hydroxide right there. Make sure to write that down. And now we can move on to part 2. So part 1, we standardize our sodium hydroxide concentration. We should figure out the molar or the molarity of that. Part 2, we're going to figure out how acidic some basic Publix vinegar is. So we're going to take that vinegar straight from the jug and measure out about 10 milliliters of it. So you can see 10 milliliters right there. And we're going to go ahead and dilute this 10 milliliters 10 times. So a 10 times dilution of this original jug. So we're going to get 90 milliliters of water into this graduated cylinder. We'll add our 10 milliliters to that 90 milliliters, thereby creating a 10 times dilution. So our vinegar is now 10 times diluted inside of this solution. Go ahead and pour that into a Erlenmeyer flask. And swirl it around to make sure that the vinegar is evenly mixed throughout the water. Perfect. Now we'll use a graduated pipette to take 10 milliliters of this now 10 times diluted vinegar like so. And graduated pipettes are very accurate, which is important. So we get 10 milliliters there. And transfer that into an empty Erlenmeyer flask. Okay, so this Erlenmeyer flask now has 10 milliliters of our 10 times diluted solution, and to that, we'll just add some more water till we reach about 70 or so milliliters. Now, once again, what's important is not the amount of water, but the moles of acid, which is vinegar in our case. We'll add our phenolphthalein, our indicator, to make sure we'll know when the solution becomes neutral. And we'll go ahead and record our starting volume. So go ahead and write that down in your notebooks. And we'll start dropping our base into our acid again. So the stopcock has the same amount of sodium hydroxide, or the same kind of sodium hydroxide that now we know the molarity of. We'll start dropping it slowly into our solution of acid, or vinegar. So every time we swirl, just to make sure that we're getting an even distribution of acid and base throughout. And there we go. We've reached the end point here. You see that nice pinkish purple hue. And we can record our final volume for our sodium hydroxide. Now we'll repeat that to get a second trial. We'll take 10 milliliters of our 10 times diluted vinegar solution, put it into an empty Erlenmeyer flask, add some water, add some phenolphthalein, swirl it, and then we will go ahead and put it underneath the stopcock to start dropping the base into the acid. Here's our starting volume. Go ahead and record that in your notebooks. And we'll slowly swirl. And there we go. We've reached the end point. Go ahead and record the final volume in your notebook as well. And we've done our 2 trials. So thanks for watching.